I come from engineering and technology background, so we'll try to give you a glimpse from technology side of all these decarbonization stories, what pathways and what are the challenges that technology is bringing into that. When we talk about all the future gases, I would like to talk on two things. One is, of course, the hydrogen. It's a very obedient molecule, you know. Binds very easily with hydrogen, with nitrogen. You can utilize it in a various way. It's really an magic kind of a molecule. It's up to us to utilize it in the way we want it. Just see this flow sheet over here is a sample when we talk about green chemicals and low carbon pathways. When we are talking about any industry, be it refining, steel, cement, or fertilizer or anything, electricity is the basic need. So we have the electricity grid running across the industrial estate that draws the power to the industrial sector to make any products. We are predicting that hypothetically there will be a hydrogen grid. So hydrogen will find an application into virtually every industry that you are talking about. So this hydrogen grid may, a physical grid coming into the clusters in the industrial estate supplying hydrogen as a form of energy or as a form of a feedstock to all these industries. If you take the example, if you can use the hydrogen into the refining industry, you can use it into the cement industry, you can use it into the CO2 industry. If you are using it as a combustion fuel, it will generate CO2, and that CO2, if you again react back with hydrogen, you can produce a good amount of chemicals over there. So that remains into the circular economy. So methanol is one where everybody is interested, react with the carbon dioxide, the green hydrogen, and what methanol can do the wonders. We talked about ammonia as a marine shipping fuel, lot of discussions. Yes, methanol too can be used as a marine shipping fuel. Methanol you can convert it to dimethyl ether, again another fuel. Methanol you can convert it to olefins, that's the best technology, methanol to olefins. Lot of China plants have been available, and once you have the olefins, you can convert it to the polyolefins, polymers, and whole lot value chain is available to you to make it at a low carbon at a various efficiency. Of course, ammonia, you know, used as an hydrogen energy carrier. NEOM city project in Saudi Arabia, everyone is aware of, wherein they want to convert the hydrogen into the ammonia, ship it cross country, and split the ammonia across the Atlantic back into the hydrogen and sell that hydrogen. So there are other utilities of hydrogen. Now hydrogen is also coming up from water electrolysis, but we will see the other pathways. We have shown it over here as another important fuel which I want to talk is about LNG, and how LNG and hydrogen both find a role, and how we can utilize both of them in together and not in isolation also. I mean, we have to blend hydrogen into LNG as using hydrogen as an fuel value is a volumetric low on a volumetric density. Hydrogen has its own challenges with respect to transportation, with respect to storage. So maybe the best way we will see in further one or two slides as to how do we use hydrogen transportation, how do we use the existing natural gas pipelines available in the country for transporting of the hydrogen. The whole value chain of the hydrogen, currently we are talking about the water system, about a lot of water. If you are talking about generating it from the electrolysis and water splitting using electrolysis technology, 9 liters to give you 1 kilo of hydrogen. So this water unfortunately needs to be a DM water, so a lot of water treatment costs, a lot of water treatment technologies that may need to be support to this energy transition. Renewable energy, of course, all forms of renewable energy. Here we have done a lot of simulations. The most important part is we cannot have all our future energy thrust coming from the renewable energy. If you can see at the energy basket, if India wants to reduce our reliance on the coal and increase the share of the clean energy, the renewable energy, there is a limitation as to how much percentage of renewable energy can come to the basket of the clean energy. So we predict a lot of nuclear energy to be the future. Right now we have about 5 to 6%. That may go eventually up to 20%, because for the renewables you have limitations on the materials, the mining, the recyclability, end of the life recycling and processing. So the energy cost of return on renewable is around 30 to 35 energy returns of investment. EROI, I mean that how much energy that you produce to put that renewable energy, and in its life cycle how much energy it can give it back to you. So this EROI on renewable energy around 35 to 40, and nuclear is about 75. So you can think the potential over there. And yes, lot of storage systems, logistics, lot of technologies will come for hydrogen value chain. The future of hydrogen, we speak on three terms about generation, transportation, and its application. Let's go on as far as the generation of hydrogen is considered. Let's go beyond the water electrolysis or the green hydrogen technologies. Think of the new technologies that are coming up, but they are very less popular, available at a low TRL level. Talk about the copper chlorine thermochemical cycles, talk about the sulfur iodine thermochemical cycles. Those technologies have been developed indigenously. They were available here in India. Copper chlorine cycles are developed by ICT and BARC. Sulfur iodine cycle is also developed by BRC. There are several other institutes and researchers. Those technologies provide you, as on today, green hydrogen at the cost of less than $1 per kg. So those technologies will be the future. Look for the, learn from the nature, see for the artificial photosynthesis. So the catalysts have been developed wherein if you can dope those catalysts on the surface and it acts as an artificial photosynthesis, giving you the hydrogen at a much lower cost. So those are the future of the hydrogen generation. As far as the storage are concerned, look for the caverns, look for the metal hydride systems, look for the physical adsorption and absorption systems, especially for the transport sector. Go beyond the type 3 and type 4 of the expensive pressurized gaseous storage, and look for the hydrogen into the solid form is what the future of the hydrogen storage lies into. As far as the transport of hydrogen is concerned, I've said that future is in blending it with natural gas, transporting it very easy along with the natural gas. I don't want to go in details about the applications, but this is one or two of the hard to abate industries. You can use hydrogen to make the green steel. The conventional steel making blast furnace and basic oxygen furnace route can be replaced by direct reducing iron DRI route, and you can have hydrogen to be used as a redundant or reducing gas over there. Plays very important role to decarbonize steel industry. Go to the road transport. Just now Amit has spoken at length about the role of hydrogen. In our opinion, our simulations say that these battery electric vehicles remain into the transition. Hydrogen will be the future, and it may be the hydrogen fuel cell vehicle not alone, but also the ICE engines using hydrogen. In India Energy Week last year in Bangalore, Reliance has already demonstrated the first hydrogen ICE engine. In California, already the hydrogen ICE engines are running. So the future will be a hybrid economy, the coexistence of multiple fuels, everything leading to the low carbon fuels. Cement is another very hard to decarbonize sector, so hydrogen you can burn here, but the typical properties and the flame temperatures of hydrogen won't permit you to use it as an fuel directly into the cement industry. So maybe you need to blend here with the biomass to get the proper adiabatic flame temperature that will suit to the cement industry. But again, it will find an application into the steel and cement and fertilizer industries, which are considered to be very hard to abate industries. In the opening session, chairman talked about converting the CO2 into the fuels. So this is one technology, very interesting and upcoming technology, which is a sustainable aviation fuel, which you can convert the carbon dioxide, react it with hydrogen and make the sustainable aviation fuel. So the reverse water gas shift reaction technology is already known. You can directly hydrogenate the CO2, or you can convert that CO2 into the syngas, carbon monoxide, and send it to the Fischer-Tropsch reactor that will give you the liquid fuels. So this is one of the very promising technology coming up. When you talk about sustainable aviation fuel, this is an alternative to making it from fatty acids, lipids, or cooking oil, or even from alcohol to jet. Though they are maybe a little cheaper than CO2 to SAF, but that comes at a very large economic penalty. So converting into the useful fuels, capturing the carbon dioxide, you get the double benefit over here. And this we see a traction coming up in near future, and this hydrogen to SAF will see a good ammonia. I won't spend much time on hydrogen to green ammonia. There are other forms of energy carriers. A lot of things have been talked about the toluene and methyl cyclohexane also as an energy carrier. This technology is also available. So you hydrogenate toluene to make methyl cyclohexane, transport it, and split methyl cyclohexane to get back hydrogen to you. So apart from ammonia, there are other technologies that are also available to work for this. There is, as far as the natural gas blending with the hydrogen is concerned, everybody considers this hydrogen is having a very great energy, but its volumetric energy density is unfortunately very poor. So when you start blending hydrogen into the natural gas, in fact, its net heating value starts coming down. What we call it as a Wob index. Wob index is the measure of the fuel, wherein we can find out the alternate fuels if you can mix, if you can substitute. The Wobe index of the fuels, if it matches, then you can substitute or you can mix. Unfortunately, the Wobe index, when you start blending hydrogen with the natural gas, will start going down, and we need to find out the optimum blend percentage at which you can use the blend of nitrogen and fuel gas as together. We start with 5%, 10%, up to 20% people have used it. It has got a lot of impact on the metallurgy that you are using. Hydrogen is a very peculiar case. Hydrogen embrittlement happens. The stress corrosion cracking and hydrogen induced cracking. The surface cracking, penetration of hydrogen into the metals is a deeper phenomena that is that stops blending the hydrogen to an infinite extent or by 100% extent. But however, 5 to 20% is the safe range, depends on what pressure and what conditions you are using the natural gas now. The breakthrough idea over here and the technologies that are being developed is to remove this percentage limitation. Say there is 33,000 kilometers of natural gas pipeline available in India. I start purging 2% or 5% hydrogen into that from one source. You transport it cross country, thousands of kilometers, and at source I get this blended mixture. I put a membrane, separate the natural gas from hydrogen, and use the pure hydrogen as free. So those technologies are also available. So I can use the effectively the pipeline network available in India for transporting the hydrogen, removing the limitation of hydrogen transport in liquid form or in any other organic carrier form, or it is you can transport it the way you are transporting natural gas. That's what is the future that we see. Of course, this CO2 reduction when you blend with the hydrogen content, the more the blending percentage, the CO2 reduction will be very higher. We are talking about the 10 or 20%, it will be hardly 7% CO2 reduction. Still it is a low carbon economy, still it is a transition data, till everything has been fully developed and you switch from fossil fuels to low carbon fuels to zero emission fuels. This is what the percentage will look like to increase as you keep on increasing the blending percentage over there. We talked about this effect of embrittlement, that decides how much percentage you can blend it over there. Lot of challenges in hydrogen blending in the existing gas network with respect to safety, with respect to material properties, with respect to infrastructure upgrades and things like that. But as we start doing the experimentation, I'm sure that it will find a better optimum mix, and we have to start from somewhere, start from 2%, start from 5%, increase it gradually and go to 10 or 20%. Or those challenges, the technological solutions are definitely available to meet all those technological challenges. That's what I would like to limit and give you as an overall perspective of where we see the future of the low carbon economy within the transition, and whatever are the energy gases we definitely cannot ignore hydrogen and natural gas. Just one comment I want to make over here: the bigger challenge, energy transition equation, is not very easily solvable. As we are growing population, our GDP is growing, our energy needs will also grow. Now, to meet the energy demand and reduce the emission, that itself is an imbalance into the equation. So all these technologies, all these future technologies will aid to solve this energy transition equation. It may be 2050, it may be 2070, but in 2024, I urge all these stakeholders to start thinking and implementing these technologies from pilot scale and gradually scale it up, so that by 2030, we have a very substantial things to show with respect to the decarbonization of Indian industry. That's what I will rest my case.
Thank you very much, Mr. Choudhary.
Yeah.
Any questions, please? Yeah, please.
So yeah, thanks for the presentation. I was just wanting to know the view of the industry on small-scale hydrogen production or ammonia production or methanol production. Like, I'm not talking about the world-scale ammonia plants or like 2,000 tons per day or something like. Because in India, like, there would be a resource constraint. Like, are there any like emphasis on the small-scale ones?
No, there is. See, till the costs are coming down and the technologies are fully matured, and it is expected that the economies of scale would help to bring down the cost of green hydrogen or green ammonia generation. But in the interim, all the experimentation, the technology proving, and till the full user demand is created and fully developed, the small scale is the way to go, and a lot of things will happen in clusters, in isolated places, in a decentralized manner. One, to prove the technology; second, to create the user; and third, to start capturing this part of the energy markets. So beginning with, I agree, the small scale will grow faster than the large scale.
Yes, please. There, please. I think these challenges, what Mr. Choudhary has pointed out, really makes it a scenario where hydrogen is produced locally or used locally there itself, But then there are larger challenges. We solve those challenges, then only perhaps hydrogen usage would grow. Yes, please.
I want to know about the safety aspects of blending. These different percentages are blended and in natural gas, and then you want to use it in the gas grid.
Yes, there are a lot of parameters you need to look from safety.
It's a real challenge. I want to know, have you studied the percentage versus the safety aspect of blending?
Yes, see, with respect to safety, you have to consider this overall safety of the transportation system. Hydrogen and natural gas are two different molecules with respect to its heating content, with respect to its molecular weight, with respect to properties, with respect to densities, with respect to combustion limits, with respect to leakages, with respect to corrosion, with respect to compressibility factor, with respect to power consumption, with respect to corrosion allowance, with respect to life. Various things go when you decide up to these blending percentages, and you have to evaluate the health of the existing pipeline system considering all these parameters.
Yes. This safety has to be the prime objective.
Right, that's right. Okay, sir.
Thank you very much.
Thank you everyone.
Wonderful, very nice.
Thanks all.
Thank you.